and welcome to this manufacturing systems technology part 2 module 14. We were talking about the 7 tools of QC and we had already discussed earlier the histogram, the Pareto diagram, the cause and effect diagram and the check sheet based methodology of recording quality. Today we will focus on 3 more different aspects. One is the defect concentration diagram, the scatter diagram and the control charts, which again would have a very detailed introduction and analysis as to how these are to be plotted because it is really giving a real time sense of control of quality on the process level. So let us look at the defect concentration diagram. A defect concentration diagram is a visual representation of the unit under study showing all possible views with possible defects identified on it. The type of representation is useful in understanding the type of defects and their possible causes. When we look into an automotive unit, we will have different views of the automobile. For example, let us say when we are talking about the roof of a particular car, this can be related to something like this kind of an aspect, and one of the possibilities is to sort of review the various related areas of this particular module and try to understand the defects in terms of the modules related to this particular car. So a person may say that there is a dent on the roof, for example, so he will identify this as a roof dent. Or for example, if he says that the level difference here between the door and the body, between door and body is improper, so he will represent exactly what area of the car. So there are many views. There may be a view from this side, there may be a view, as you can see, from the top or the left of the car or even the front body. There can be also a view towards the back door side, which talks about something like this kind of a view, and there can be something related to the back door saying, let us say if there is some kind of a paint peel off in this particular region. So the operator now, so there would be various views in a check sheet. So there is a check sheet like this and there are different views, and the operator can actually represent the location of a particular defect and then give that this kind of a and record what is really the type of the defect which is recorded on the check sheet. So then visually it becomes very easy for the repairman to quickly isolate and go to that particular area where the particular defect would be present and be able to repair. So one of the reasons why defect concentration diagrams are given is to really quickly realize and identify during the repair stage the exact location and the exact nature of the defect, because obviously the repair happens not within the assembly line but offline, and slowly there is a there is an initiative within all automobile majors to sort of pump in all the inspection as well as repair to online rather than offline, so that less time can be wasted. But that is actually a far-fetched dream from reality. It is really dependent on the correct process quality control. But as of now the situation is that typically all the auto majors have they do not jeopardize their production rate because of the presence of a defect which is there in the system, and rather would like to make a separate repair area where these vehicles can be clubbed up and slowly repaired before sending it to the vehicle inspection or the VI of the particular shop floor. So here also in the defect concentration diagram, it is sort of giving an easy way of representation and communication between the inspection representative and the repair representative, so that there is no time delay because of non-understanding of whatever has been written by the inspector on the particular check sheet. So that is about the defect concentration diagram. There are also diagrams which are called scatter diagrams, and typically it is useful in establishing a relationship between two variables. The shape of the scatter diagram is obtained by plotting the two variables. It may indicate a positive or a negative correlation between the variables or no correlation at all, and such information is helping sometimes in developing a control strategy for these variables. For example, let us say we look at a scatter diagram here. This is actually representing the current versus the time, you know, of a certain process. Let us say for example you can see that the base current here is in picoamps and the time of response of the particular circuit is in, let us say, milliseconds, and you can find out that typically there is a lot of scatter on a certain situation where there is a lower time of response and considerably higher current, you know, and these are the regions which probably show that there is a trend that the circuit is bleeding more current than is needed. Okay, so you can actually plot the scatter diagram to be able to at a glance sort of interpret something about the process from the inspection studies that has been done by the probably an inspector or a person recording this data in an electronics assembly line. Okay, so these kind of situations are plotted by scatter diagram. There is also a very important aspect to monitor real time the quality, which is called the control chart, and this is something where we have to really emphasize more towards process control or process capability analysis, and the control charts are very important because they help in reducing the variability of the quality characteristic which is of interest. And if we really were to classify the overall variability of a process, there may be a situation where the variability causes or arises because of different aspects related to the process. One of them can be the chance causes. There may be some randomness in the way things occur at the process level which may create some kind of variability between the products, or the other aspect can be assignable causes where there is a certain reason which can be framed back for a certain non-conformance in a quality characteristic. For example, if an operator is new on a particular station and he is doing some kind of a fitment where there is a recorded problem, because of his untrained nature he may be able to create this defect in the particular assembly in question, and so the idea is to be able to identify the operator and train him well so that there is a increase in the quality aspect. So who will control this, and therefore there is sometimes a statistical control which is available along the length and breadth of the process, which is called the control chart. So the variability in the process is due to a cumulative effect of many small but essentially unavoidable random causes. A process is said to be in control only if the chance causes are sort of present in the process. However, there may be other causes of variability that may create a shift in the process to an out of control state, resulting in a significant portion of the output not conforming to the specification which has been laid out, the ones which are known as the assignable causes. And how do we plot this control chart is a very critical issue. So here a typical control chart would be a sort of a graphical display, and this would sort of display a certain quality characteristic which is either a measured quality characteristic or maybe visually acceptable unacceptable kind of a quality characteristic. But again you can plot both the aspects in different manners, you know, and so let us talk about, let us say, the measured quality characteristic aspect on a sample. So there is a sample number and these samples have all been inspected and a quality characteristic has been measured within these samples, and what you have to plot on the control chart essentially are three different elements. One of them is a center line which represents the average value of the quality characteristic corresponding to the in control state out of all your observation which is there. Let us say you are observing 100 samples out of 1000 which are being produced, so 1/10, about 10% is inspected, and in this 100 samples you have an average value which is recorded. When you are talking about a diameter of a shaft, it may be the diameter of the shaft measured in those 100 samples which cause a certain mean or a certain average value of that 100 samples being recorded as a center line. So that is the center line, and then you have an upper control limit which is represented by a upper horizontal line probably parallel to the control line or the center line of the chart, and this sort of represents the deviants from the average which are there or which are present in the distribution. Okay, and then there is of course a lower control limit as well which is represented by a line below the central line. So the idea is this, you have to very clearly understand, is related to the process variation or the process capability. So you have a center line, you have a upper specification limit, you have a lower specification limit related to the production that is being done in the process, and then when you need to estimate the capability of the process toward a certain design, you have to illustrate the specification on the design and see whether those specifications are lying within the process or vice versa. If the specifications which are mentioned are out of the process, you can easily say that the process is very well controlled and can be used very accurately to render the deliverable quality which is being intended in terms of the design specifications which are there. So we will come to that comparison a little bit later, but right as of now you have to understand that what we are plotting here is only the production related issue, that what is the central tendency of the production, what is the mean characteristic of the production. If you are talking about the diameter of a shaft, what is the mean diameter of that 100 samples that you have recorded, and then an upper limit which would correspond to the maximum diameter which is recorded in these 100 samples, and a lower limit which is recorded as the minimum sample diameter which is recorded on those 100 samples. So this way you draw the UCL and the LCL. So the selection of the upper and lower control points also depend on the notion that all sample points should fall between them if the process is in control, and the points lying outside these limits signal the presence of the assignable causes. So obviously now you have a control chart in place and you are observing these samples for n number of or for a certain period of time, and the moment there is a deviant or an outlier to this control, you are able to quickly record that there is a reason why the process is going out of control, and then you take a countermeasure so that it comes back in the control. So that is the real time analysis of the process health. You can say it is a process health monitoring system that you are building with the time, so that you can always in a very small cursory glance determine whether the process is in control or the process needs some kind of a quality improvement so that it can come in control. So the process should be investigated from time to time based on the control chart data to eliminate these assignable causes of variation and bring back the process to the normalcy. So how do we really plot? So you have let us say y, which is a sample statistic that measures some quality characteristic of interest, and let us say there is a average mu y and a mean sigma y, which is the standard deviation. So obviously the CL, the center line, would be about the mean, and the UCL would be about mu y plus some factor k times of sigma y, and the LCL similarly would be minus k sigma y on the mu y, and k is actually the distance of the control limits from the center line. So if I was to say that k is equal to 3, we are talking a control of plus minus 3 sigma between which the control is being executed. Okay, so on the upper side you have 3 sigma as your plus 3 sigma as your upper control limit, and minus 3 sigma on the lower side as your lower control limit. So having said that, the control charts are categorized into again variable control charts and attribute control charts based on if you are talking about a measurable variable or something which is like a quality attribute which can be recorded as acceptable or not acceptable. So there are many such quality characteristics. Let us say for example the polish on a surface of an automotive, it cannot be measured by directly, although it can be probably as a function of the gloss or the reflectance of light, but when we are talking about a situation where there is a minor variation in polish which only the human eye can record, you will actually qualitatively investigate that as polish being acceptable or not acceptable. So there is no measurement as such involved in those kind of classifications, and they are known as attribute control charts. A variable of course you have done before is related to let us say the diameter or some other measurable characteristic of the particular product, and there is a measurement which is involved and the data of the measurement which is involved which is used for recording the control chart. So these are the typical classifications of the control charts. So I think I will stop this discussion here on control charts and probably begin again in the next module in the interest of time. So in the next session we will look at very closely and investigate more related to how do you really statistically find out from a distribution the mean, the standard deviation, so on and so forth, for recording and plotting these control charts. Thank you.